Hi, I'm Brian Wable, and we're going to take a quick dive into wet thermistors. The objective here is to determine the relationship between input and output by statically and dynamically calibrating the wet thermistor and observing characteristics such as sensitivity, time constants, and total uncertainty. So what exactly is a wet thermistor? Well, a thermistor, as seen in its name, is a thermal resistor. It is made up of metal oxides and changes resistance as temperature changes. There are two types of thermistors, negative temperature coefficient and positive temperature coefficient. With a negative temperature coefficient thermistor, when temperature increases, resistance decreases. We will be focusing on these thermistors. For the setup, we need to create a voltage dividing circuit so we could read in the voltage drop across the thermistor. You could also do the excitation voltage minus the voltage drop across the non-resistor if the setup was easier. A lab UVI was also utilized to record that data using a MIDAC. For the static calibration, the wet thermistor was placed in a beaker of water. The beaker was heated and the voltage drop across the thermistor was recorded for every 5 degrees Celsius change, starting at 25 degrees Celsius and ending at 90 degrees Celsius. The data was recorded using a MIDAC and lab UVI from National Instruments. The data was also cross-referenced with thermometer reading that was also recorded. For the results of the static calibration, we see that the change in resistance varies with temperature. This goes to solidify our knowledge that the thermistor has a nonlinear relationship among resistance and temperature. The data is then plotted for resistance versus temperature and voltage versus temperature to display nonlinear curves. By using a polynomial fit of degree 2 on the data for voltage versus temperature, the data is able to be fitted and certainties can be found. Above you can see the errors and uncertainties for the static calibration. The curve fit error is a result of the difference between the fitted data from the second degree polynomial and the raw data. The temperature error is a result of the error from the thermometer. The quantization error is a result of the error from the MIDAC. All these errors lead to the total uncertainty. For the dynamic calibration, the wet thermistor was dunked into a beaker of water. The response of the system was then recorded using a MIDAC and lab UVI. The dynamic calibration was plotted to visually display how the thermistor responded to being dunked in water. By using a z-plot to transform the data onto a logarithmic axis, the time constant was able to be found. The time constants can be viewed above for each dynamic calibration trial. That's all, folks. Thank you.